Hello everyone, my name is Pranav. Today I'll be talking about a paper on a unified image demosaicing and rectification method, which we call Splatty. Demosaicing and rectification are key tasks that are part of most computer vision pipelines. To date, however, their implementations have had high memory requirements and inconvenient data flows, making it difficult to scale them to real-time, high-resolution settings. In our work, we demonstrate a unified pre-processing pipeline which reduces the memory footprint by almost an order of magnitude without compromising on the image reconstruction quality. To explain our pipeline, I'll first provide an overview of the underlying tasks. Demosaicing is the process by which raw, monochrome data from the camera sensors is converted to an RGB image. Rectification is the process of warping the input images to correct for camera misalignments and to correct for optical distortions such as lens distortion. Both demosaicing and rectification involve some form of interpolation, and two consecutive interpolation steps can result in unnecessary loss of information. Our algorithm performs both demosaicing and rectification in a single interpolation step, and as such, leads to a better image reconstruction quality. Usually, rectification is performed using backward mapping, where for each pixel in the output image, we find the corresponding subpixel level location in the input image. We compute the intensity at the subpixel level location from the intensities at its pixel level neighbors. We assign this interpolated value to the pixel in the output image. This is a simple yet effective method, but it does not work well in a streaming setting, where we need to buffer the input image and only store a few rows at a time. In contrast, we use a technique called forward mapping, where for each pixel in the input image, we find the subpixel level location in the output image where it would land, and we contribute a fraction of the intensity of this pixel to one or more of its pixel level neighbors. This fraction is usually a function of the distance between the subpixel and its pixel neighbors. The final intensity at each pixel in the output image is usually a weighted sum of the contributions of intensities from all the pixels which landed in its neighborhood. This method is slightly more tricky than backward mapping case, and Splatty needs to be done correctly, otherwise some pixels get no contributions and leave holes in the output image. However, if done correctly, this method is well suited for the streaming settings since we only need to store one row of input and only a few rows of the output at any given point of time. We extend the forward mapping based rectification approach to combine rectification with demosaicing, where each pixel in the input image contributes its intensity only to its corresponding channel. When one row of the output is done, we refine the intensity estimates of the three channels using their initial estimates in a manner similar to some of the earlier demosaicing methods. This way, we get an optimized pipelined approach which needs to buffer very few rows at any given point of time and reduces the memory footprint without sacrificing the output quality. To reduce the memory footprint even further, we compress the lookup tables by fitting polynomials to each row or column of the lookup table, depending on which is smaller, and storing the coefficients. The decompression involves minimal computational overhead since we only need to compute the value of a polynomial at a given x or y using the coefficients that we have stored. This method allows us to compress the lookup tables from an m cross n size to a linear size. We also see that the compression error is pretty low using something as simple as a sixth order polynomial. One of the most widely used memory-efficient demosaicing methods is the high-quality linear interpolation algorithm by Malbar, He, and Kusher. Through demosaicing results on the widely used Kodak dataset, we show that our performance is as good as, if not slightly better than theirs, while keeping the memory utilization way lower. We also compare our reconstruction accuracy versus the memory footprint against other methods by simulating a demosaicing and rectification pipeline using the most efficient rectification method as a label and the top demosaicing methods in use today. We see that we far surpass any other method in terms of memory utilization without sacrificing much in the reconstruction accuracy, as measured by the average peak signal to noise ratio on all the images of the Kodak dataset. Memory utilization is an important metric because if methods cannot fit in the on-chip memory of the system, then we need to store the intermediate results in off-chip memory, and the read-write latency involved in that will render the pipeline too slow to be feasible for real-time, high-resolution settings. And even for methods which can fit in their memory, less memory usage is better, since we also need some memory for downstream tasks like feature matching and tracking or SLAM. That's why our proposed system is so valuable. Because memory utilization is so low, our system can work at higher frame rates and with higher resolution images than any other system. Thank you for watching our video. If you want to learn more, feel free to check out our paper or visit our website.